Thank you all very much for coming today. And the purpose of my presentation is to introduce you the subject area of microbenchmarks. Here is my email, and feel free to send me a message anytime you want. Okay, so let's start. Let me briefly introduce myself. At first, I'm a Java developer, probably like you. And I'm related with PayU, part of Allegro Group, when I am working as a head of software developers. And in PayU is like dragons, so we've got 3 heads, one in each town we are running the development. And I'm responsible for software development, proper selection and use of tools for development and versioning. And privately, I'm a huge fan of Java util concurrent package and unsafe class. Unsafe is a class that provides almost unlimited capabilities of exploring and modification of virtual machines' runtime data structures. So it allows to direct access to memory, compare and swap operations. You can even inherit from string class using the unsafe operations. And after work, I spend my time gliding near Krakow, and I'm also a contributor of LK 8000 navigational software, unfortunately written in C++. But okay, so you can ask why do we in fact need microbenchmarks? And I can bet that a lot of us faced some performance challenge. For example, should I use an array list or linked list? Or what buffer size should I use to access my files? And it seems that microbenchmarks are very easy. It just start the clock, execute some code that we want to measure, and then stop the clock. After subtraction, we will get our result. But there is always a but, and the same but we can find in microbenchmarks. It's very easy to get fooled by microbenchmarks, and it's hard to get the meaningful results. It's not so easy to know what have we exactly measured, and I will show it on the examples later. And the another problem is that there is no great tool solving all problems which can we find in implementing microbenchmarks. My presentation is divided into a few parts. Firstly, I will show you a very sample microbenchmark, and we will see what is the result of its execution. Then I will talk a little about JVM internals, some JIT optimizations, and so on. And I will mention some of the problems we can encounter while implementing the microbenchmarks, and I will try to say you how to overcome them. And if there will be any questions you'd like to ask, please leave them until end, and then if we have time, I will do my best to answer them. Okay. That's very simple example of microbenchmarks. Core of this snippet are 2 loops, and in the inner loop we are counting the square root for some index. And what do you think? How long does it take to execute this code? It's over 1 billion iterations just in the outer loop. So no, not so fast. 2 milliseconds. Wow, it's pretty fast for me. And I think there could be only one explanation, and technology borrowed from UFO. But how many of you believe in UFO? No, no one. Okay, so I will try to say you from what these 2 milliseconds come from. All right, so start from a little bit of the theory. I will talk about how JVM is constructed and what stems from its architecture. So this graph shows you one of the many available approaches to the JVM architecture. And we've got here runtime. Runtime loads code from class files, and it's also responsible for garbage collecting. And after loading this code, we have interpreter. So method is executed in an interpreter. And when the execution count crosses the certain threshold, then JIT transforms this method into the machine code. And there is also another way of transforming bytecode into the machine code. It's called OCR, but I will talk about OCR later. There is also the optimization, and the optimization, we'll look at it in more detail later. There is also big heap on this graph, and this heap is referenced bothly by machine code and the bytecode. So, move on. Just-in-time compiler. So I have heard many myths about it, and it is also called dynamic translation. And as a tidbit of news, hotspot name is owed to the JIT, because JIT is profiling some methods, and when he spots that this method became hot, so the execution counts crosses the certain threshold, then he optimized. So he's spotting the hot method. So hotspot is named from the JIT. Okay, so Java compiler produces really dumb bytecode and trusts the JVM to optimize it on the runtime. We have got also ahead of time compilers like GNU compiler for Java or LLVM from Apple, and they are optimizing the code just in C++, so on the compile time. And JIT is working in the runtime, so it's very important to understand it. I will show it later. JIT's very lazy. As I said, it's starting to work only when the method gets hot. So the threshold of 10,000 invocations is the standard flag on the server JVM. So we've got minus server and minus client flags. Do you know what is the base function of these flags? Okay, it's not setting the default heap size and garbage collector. The main function of minus server and minus client is to switch between two implementations of JIT. So server JIT called C2 and client JIT called C1. And on the server JIT, the threshold is about 10,000, and for client, as I remember, it's 1,500, so it's a lot less. Okay, also, what is important with JIT? JIT runs on class files, so it applies also for Scala, Groovy, Clojure, and any other language that is run in the Java virtual machine. And it's not so important in the context of microbenchmarks to know all JIT's algorithm, because there are over 60 main performance techniques used by JIT to increase the software speed. And there are also very significant differences between different vendors. So JIT in JRocket is different than JIT in Hotspot and different than JIT in IBM virtual machine. And JIT code runs many faster than the interpreter. So it's efficient machine code. And another thing, JIT is taking almost only heuristic decisions, so he can go wrong. Or the circumstances of our application can change. For example, I can have a monomorphic code, and after loading some new class, my code changes into polymorphic. So JIT has to de-optimize, to roll back this all the optimizations he done before. So it's very important to know that it's no all or nothing process. Inlining. Inlining is, I think, the most important optimization in JIT. In simple words, it's getting the cold method body and put it into the colors method. So why? Because more code gives us much better visibility. I will show it on the examples later. And another important thing is that we have got two important flags of the JVM reference to the inlining. So max inline size, it's the maximum size of the bytecode for the method we want to inline. And it's too small, and on production, it's good to change it to for about 100. And minimum inlining threshold. As I said before, there is a global threshold in the JIT, but for inlining, it's decreased to 2.5. So I have heard a myth from one of the developers that it was some time ago. He said that he's not using getters and setters because they are introducing overhead. So there are only public fields because he wants his code to be very optimal, very speed, yes? And as you can see, the first thing that JIT will do after executing some methods, he will inline those getters and setters. So there is no overhead, so fortunately we can still use encapsulation. So it's, oof. Okay, dead code elimination. It causes the greatest problem in implementing microbenchmarks. And in simple words, microbenchmark is code that has no effect on the result. And dead code elimination is quite useful in real code. And not that because developers are writing intentionally dead codes, but when the compiler discovers some dead code due of inlining, he can replace, for example, variables with constants, because he can see that this variable is in test is in fact constant. So it's very hard to predict where the DCI, so dead code elimination, will happen, because mostly of the inlining and other optimizations. And dead code elimination can also extend to control flow. And it makes it tricky to make microbenchmarks trick enough to actually time what you think you are actually timing. Compilation. It's the thing we have seen on the first diagram today. And it's JIT compiles this method bytecode and transforms it into the native code. And it can boost up, so speed up our code up to 20 times. So it's pretty powerful optimization. And after compilation, JIT continues profiling. And as I said before, he may recompile the code again later with a higher level of optimization, or if it decides that this code path is particularly hot, or future providing data suggests opportunities for additional optimizations. So it's continuous recompilation. And there is also another point in this slide, and it seems pretty obvious that only new calls follow the new path. So I cannot switch in the middle of execution from the interpreter to native code. But this is surely a limitation, but JIT can do something with it. Have you heard about on-stack replacement? Yes, some people heard. Okay, so on-stack replacement allows a loop running in the interpreter to transfer control to a compiled version of this loop in the middle of execution. So when the loop gets hot. So I can have, for example, one main method and big loop in this main method. This main method will be executed only once, so no JIT optimizations on this method will be proceed. But this, if this loop will have many iterations, for example, 40,000 iterations or something like that, then only these loops will be compiled into the native code, and it will be replaced on the stack, and the next iterations will be proceeded in the machine code. So every loop's body is a potential entry point or potential trigger for doing the on-stack replacement. I must introduce term bytecode index. Bytecode index is a place in Java method. It can be compared to the line number in the source code. So I can have many versions of the OSR method as long as that bytecode index differs. It's another quite powerful optimization. Escape analysis. So many objects in Java doesn't survive a particular invocation scope. So dynamic determining scope for this object is called escape analysis. It can result in, for example, object explosion. So I've got method and just method. And in this method, I'm instantiating a point object. Point has got two doubles, x and y coordinates, and JIT analyzes that, and he said, hey guy, this point you are allocating is needed only in this method. It isn't escaping anywhere. So I won't strictly allocate this object. I will allocate only its components on the stack, not on the heap. So huge impact of the performance. And it does not replace a heap allocation with stack allocation. It only explodes objects. And it's important to know that escape analysis in Java 6, as I remember, is enabled only by doing setting the aggressive opts flag. Okay. In fact, escape analysis can also eliminate locks if the monitor is not reachable from other threads. And scalar replacement is similar to object explosion. There's automatic stack allocation. And there are some other techniques of JIT. The first called loop unrolling. And loop unrolling is, for example, when I've got an enum and I've got values for this enum and I'm iterating for these values, and compiler knows that there are always only these 3 values. So he can unroll this loop and give, for example, 3 independent linear invocations. So do something with the first enum value, do something with the second, and do something with the third. Okay. Load cursoring. It can join adjacent synchronized blocks on the same object. So when I've got synchronized block, some code after this synchronized block, and another synchronized block synchronized on the same monitor, it will be joined into one big block. Okay, and the type sharpen. Type sharpen can replace interface with direct method calls for method implemented only once to eliminate calling of the virtual functions overhead. So to give you an example, let's look on some real code. Okay, it's quite easy, I think. We've got a supplier interface. Do you know Guava supplier interface? It can be used, for example, for time provider pattern in unit tests or something similar. Okay, so we've got class string supplier, which implements the supplier with the generic type string. We have got value here, constructor setting this value, and getter. I've got also some business method, which is doing this instantiating supplier and invoking get string from supplier, and here is some null check and returning the values from this supplier. So the first thing, okay, maybe not first, do not attach yourself to the optimization order, because the purpose of this example is only to illustrate how JIT can behave. It's not said that he will behave exactly like that because of heuristic decisions I've said before. So I've got here my get string from supplier method, and what can I do with that method? Inline it. Okay, so let's look how this code will look after inlining. Okay, so what's happened? The method that gets string from supplier has been inlined and put it right here. Okay, so now another thing that I can do. It's supplier interface, but I'm always instantiating the string supplier. So I can switch it to the direct call. Yes, so type sharpen. Okay. Another thing. I can inline it. Yes? Because I know that this string supplier, this get method, always refers to the value. So I can inline that thing, and my code will look that. Okay. So let's add another method, check not null. It isn't a dead code, yes? It's not a dead code. But what will happen after inlining? There is also no dead code. I can't be sure that check not null is a dead code. I don't know what check not null is really doing. And here also no dead code. Value can be null. Okay, but what's happened now? Is it a dead code? Yes, so in fact, after inlining, I see there is a dead code. So what can I do with dead code? Eliminate dead code. So no dead code. Great. And is it all that JIT can do? No. Escape analysis. I know that this string supplier isn't escaping anywhere. It's just living in this method's body. So I can replace it in scalar, and that's my final code. Maybe this method also will be inlined in the different part of code, but we have looked how JIT works and how it's hard to think like a JIT, to not get fooled by microbenchmarks. I have to introduce another element, so time measuring. We know that there is something like precision and something like accuracy, but are they related or no? Okay, let's say I've got a steel tape, and the precision of this steel tape is 1 centimeter, so resolution 1 centimeter. It's not implicating that if I try to measure the distance from Warsaw to Krakow using this steel tape, I will get the accuracy of 1 centimeter, yeah? So the same is with measuring methods. We have got two main methods for getting the time in Java. It's currentTimeMillis and the nanotime. And currentTimeMillis for modern system disaffirms what I said, because here we've got a resolution to 1 millisecond, and the accuracy is also 1 millisecond, but look at the nanotime. It's quite big differences between operating systems. I'm not sure why on Mac it's so big value. Haven't checked it. So, but is it good or bad? For example, 180 nanoseconds. Yes, it depends. But what's 1 nanosecond? It's 10 to the power of -9. So it's a cycle clock, cycle time for 1 gigahertz clock. Yes, it's the time taken by light to travel 1 feet. So light, 30 centimeters. Yes, so I think it's quite okay for all purposes we are using. Garbage collector. What is garbage collector? Everyone sees and knows, so it's not itself subject of this presentation. But what is important in the context of microbenchmarks? It's out of user's control. You cannot be sure that the garbage collector will run exactly at this time, yes? Especially pauses are really unpredictable. But fortunately, it's quite easy to track, and I will show how to track the garbage collector invocations. Another thing, class loading. The same as garbage collecting. Everyone sees and knows what is class loading, but it's what is important to know. Quiet loading is lazy, like JIT. All Java is lazy. And classes are usually loaded only when they are first time used. And the process of loading. Yeah, it's quite complex process. 3 main phases, so loading, linking, and initializing. And it's a really time-consuming process. So it have a considerable effect on our tests. So that's an overview of the JVM internals. And now I will try to say how to solve these problems I've just listed, okay? So the very important is the environment of our test. It's needed that it will be setup of this environment will be similar to production. So when your application on production runs on Linux, then don't benchmark it on Windows, yes? So JVM vendor, when it runs on JRocket, so don't benchmark, don't profile it on the hotspot, because there are other flags, other behaviors, so it can't be compared. And JVM flags. There is some nice switch in hotspot JVM, so print flags final. It shows not only these flags we have manually set up, but all flags and all switches for the whole JVM. So it's very useful to determine what is actual behavior in that version, in that particular JVM. And environment overhead. It's very important to no play Diablo 3 during execution of microbenchmarks. The same as watching YouTube. It could rise up the CPU utilization, I/O, and memory footprint. Yes, so we have to get the stable and not overhead environment. Warm-up. Warm-up is very important for sportsmen and is also very important for benchmarking in Java. It's quite important to determine the required duration of the warm-up phase. So we can do it using the print compilation or log compilation flags. It shows all things that JIT is doing in the current time. And I will show how to use it in, for example, Caliper. But we have to be sure that all optimizations that JIT is doing are in the warm-up phase. So during the proper test, there is no JIT's executions. The same branches as in the proper test. The best option is to use the same method in warm-up as in the main test, because when we switch to another branch, so this if statement will behave in some other way, so then JIT can introduce new optimizations. So do more and shorter warm-ups because of the OCR. And OCR, it's happening very often in the benchmarks, but only rarely in the production environment, because the composition of the code is much better on the production, I hope, than in the benchmarks. So be careful about OCR. And last thing, class loading. It is very important to load all classes before executing the proper test. And we can use, for example, class loading mxbin and invoke get loaded classes count or something that something similar method, and to see if the classes count has changed during the proper test. Okay, that code hazard. It's always good to print the results, because when something is going to the sys out, then JIT cannot assume that it's not useful. And also reporting and some bizarre results can be caused by the dead code elimination problem. And great flag, really useful and powerful, it's the print assembly flag. Unfortunately, it can be used only with debug JVM, so debug OpenJDK, or there is Kenai project, and they are also offering the hotspot disassembler. And to show how it works, I've got code very similar to the first example. I'm getting the start time, doing some iterations, counting square root, getting end time, printing results, and printing the time of the execution in microseconds. And let's focus on the line 22. When I comment this line and execute this JVM with this print assembly flag, I will get some nice code. It can be terrifying, but it's very useful, really. It's scattered, but believe me that there is no loop. I've got line 16, so calling function and then the invoking nanotime method, but there is no loop. And with the uncommented line, this looks different, really different. And I even got my loop, yeah? You see, there's add, and this add was here in line 18. Yes, I've got adding, and the same here. It shows me the line number. So very powerful, but maybe a little bit terrifying flag. And last but definitely not least, some tips. Inline decisions can be different from run to run of the JVM. They are heuristic decisions. So also performance can vary from run to run. So it's very important to run JVM many times, and it's good to start new JVM for each test. Another thing, statistics. They are very important in the context of microbenchmarks. And counting the average and the standard deviation is a must. And good option is also to count a median. Don't be naively loyal to the results. Just interpret them. Check the distribution of this result and so on. It's not automatic, it's very manual process which should be done to get meaningful results. And a little bit about tools. We've got 3 quite good tools, and the first is Brent Boyer's framework. It's fine because it handles a lot of hotspot issues that we have listed before, and it also produces detailed statistics, but there is a problem that each run takes a lot of time, and there is weak documentation from this project, and another thing that it's not a formal project. It's only a part of the Brent's article about microbenchmarks in Java. Another tool, very friendly to users, it's Caliper from Google. It also solves many common problems like instantiating new JVM and testing on different JVMs and so on, warming up the code. But documentation of this code really sucks. It is full of illogical behavior. For example, when you are specifying run millis time, so run millis, it's not the milliseconds for that code to run, but it's only time to be taken from one stage, and we are not sure how many stages Caliper will run and so on. So you can specify run time for test for 2 seconds, and the code will execute 30 seconds. We are not sure about, but this current version of the Caliper is 0.5 release candidate 1, 1, and you can feel that it's really the release candidate for version half. Okay, and another thing is JAPEX. It's nice because it's got similar spirit to the JUnit. It also produces nice HTML reports, but unfortunately the last stable version was about 5 years ago, so it's not so young tool. Okay, so that brings us to the end of my presentation, and if there are any questions, you can ask them, or I can show you some simple demo of running Microbenchmarks. So it's up to you. Okay, so I will try to show you a demo. Okay. Okay, I've got some, it's the test using Caliper's framework. So maybe we'll go to the app. I've got some hash map, an object list. So it's an enum, I will show it in a few seconds. I also got a list of test object. What is my test object? A simple object having only value. I have got constructor getter setter equals method, and I've got also the hashcode method. It's very complex. It always returns 1. But I've also got test object hashed. And here I've got the proper hashcode counting the hashcode of this string object. Okay, so what's happening in the test? Let's here. I've got an enum. It's enum because of the architecture of Caliper. And I've got with hash value, which are creating test object hashed and adding it to the list. And the same without hash, it's test object with the hash returning 1. Okay, so here is method time collection. It's another thing that guys from Google are not using annotations because it's easier to use every public void method starting from time. So that's in Caliper. Okay, and what we are doing, there is number of iterations Caliper is using, and I'm iterating, checking if this map contains key. I'm incrementing the counter and printing out the counter. Why I'm printing out the counter? Because of the dead code elimination. So let's run it and check what will be the result. Can you see this console output from the back? Okay. So these lines here are the output from the print inlining, and Caliper is getting almost everything into his output, but he can't work with print inlining. I'm not sure why, but let's look. These methods here are all methods inlined by hotspots, so it's inlining a lot of methods. Also internal methods like array copy. You see that it's internal method by the instringed keyword. So let's look at the output. Where's my, yes, here's my output. Okay, it's okay. I will show you the output and how to check if the warm-up time is correct. Okay, just me do one thing. Okay. Okay, that looks better. And I've got here warm up. So I've got starting warm up, and those lines are the JIT optimizations. It's the JIT activity. So I have to be sure that all this activity appears only in the warm-up phase. So I'm going to the end of this warm-up, and here is the starting measured section in the real code. And fortunately, there is no JIT activity, so my warm-up period is quite okay. So I will now turn off some flags. Print inlining. Print compilation. Okay. No, the output of the print flags final, which is showing all values for JVM. Okay, and here I've got my with hash method, and the standard iteration is about 23 nanoseconds. So that's option with the correct hash, and we'll see what will be the output without hash. Okay, it's quite different. 23 nanoseconds with hash, and 23,000 without hashing. So always returning 1. So it looks like the hash map really works. So that's all. So thank you very much for your attention.